Hi everyone, good afternoon and welcome to today's webinar from the Offshore Renewable Energy Catapult. We're the UK's leading technology and innovation and research centre for offshore wind, wave and tidal energy. I'm Audrey Bowie, I'm a senior project manager in the Catapult's research and disruptive innovation team, and I'll be hosting today's webinar. So the session today will last about an hour and we'll focus on one of the most innovative tidal energy projects underway today. Can I also just note to everyone that this webinar is being recorded and will be posted on our YouTube channel after the session. So the ELEMENT project, which stands for Effective Lifetime Extension in the Marine Environment for Tidal Energy, is a €5 million project funded by the European Union's Horizon 2020 programme and is led by Nova Innovation. This project brings the Catapult team together with Nova Innovation, Strathclyde University and a consortium drawn from across Europe and the UK. I'm joined today by some of the team here and we're going to explain the project's core innovations, goals and progress since it launched just over a year ago. The agenda for today is, first of all, we'll spend a few minutes setting the scene on tidal energy and the ELEMENT project. Then we'll go into some more detail on ELEMENT's goals and innovations. And finally, we'll have some time for Q&As at the end. So please feel free as we go to post your questions in the Q&A section on the Zoom menu options. So if I can now ask the rest of the panelists to please switch their videos on and we'll do some introductions. If we can start first with Colin Walker.
Hi, good afternoon everyone. My name is Colin. I work as an electrical engineer for Nova Innovation. Previously in my career, I've worked in utility scale power generation and production engineering in the manufacturing industry. But my role now at Nova includes the design of our tidal turbine electrical systems, as well as managing test and development of turbines within Nova's research projects. And in the ELEMENT project, I'm the technical lead for the system design work package.
Thank you very much, Colin. And then we'll move on to Dr. Hong Wei.
Hello everyone, I'm Hong Yue from University of Strathclyde. I'm from the Wind Energy and Control Center based in the Department of Electronic and Electrical Engineering. In the ELEMENT project, we are mainly leading work package 6 on behavior modeling, and we are also involved in several other work packages. Thank you.
Thank you very much, Hong. And last but not least, John Walker.
Good afternoon, I'm John Walker, a project engineer at the Offshore Renewable Energy Catapult based in Glasgow. Background is in the aerospace and renewable sectors and worked on a variety of projects covering gas turbine analysis, research into the impact of marine biofouling on tidal turbines, and also the design and certification of a novel wind turbine blade technology. I now lead the technical delivery on a variety of projects at the Catapult to support and develop future offshore renewable technologies, and this includes a technical lead role for the onshore testing work package for the ELEMENT project.
Brilliant, thank you very much, John. So welcome to our panel and to all of our attendees. So we'll start off with the scene setting piece for tidal energy and ELEMENT, and if I can ask John to start the introduction on that.
Okay, so I'm going to start off this afternoon by looking at the state of the art of tidal energy in the UK and also Europe more widely. So tidal energy exploits the natural ebb and flood of tidal waters. It's predictable and it's a sustainable energy source. And the key drivers for developing it are mainly to reduce emissions and ensure security of the supply. Tidal energy has the potential to supply 20% of the European energy demand by 2050, and 50% of this resource is found in UK waters. The current UK resource estimate is more than 10 gigawatts, and in practical terms, it's currently estimated that this could be up to 30 terawatt hours of energy every year. There's a significant contribution of tidal energy around the UK coastline due to its geographical position between the Atlantic Oceans and the North Sea. And 80% of the UK resource can actually be found at 10 key sites around the UK. So these are predominantly in the Channel region, such as the Channel Islands, up into the southwest region, into the Irish Sea and around Pembrokeshire, Mull of Kintyre, and then up into the Northern Isles, particularly Shetland and Orkney. The area up around the Pentland Firth is probably one of the best tidal stream resources in the world, and 30% of the UK resource is found here alone. And also some key sites around Brittany and in France as well. Faster currents of up to 5 meters a second are found at these sites, and these are magnified by topographical features such as headlands, inlets and straits, or by the shape of the seabed as it passes through narrow channels. Within Europe, the UK and France in particular are currently leading the way for developing tidal stream projects, but the USA, Canada and China are catching up through increased support and investment. And the key sites in those areas you may have heard of, such as the Bay of Fundy, Puget Sound and around the Southeast Asian islands. Currently in European waters, there's 10.4 megawatts of installed tidal stream capacity, and there's approximately 1 gigawatt either in consenting or leased. Next slide, Audrey, please. Okay, I'm going to take this opportunity to differentiate between the different tidal energy typologies, which are covered over the broader term tidal energy. So they're split up into kinetic options from the tidal stream, and also potential energy options which you'd get in a tidal range, such as a barrage or a lagoon. Images here are shown for illustration of the types and are not by any means the only devices available. There's actually up to approximately 100 different tidal devices at different stages from concept through to deployment. So what we're going to be looking at within the Element project and more widely today are the axial flow and horizontal axis turbines that you can see on the top left hand side. Particularly you can see Nova Innovation's turbine. Okay, next slide please, Audrey. Okay, so technology readiness. So the technology is now crossing a boundary between from demonstration projects into commercial tidal arrays. In the last decade or so, there's been significant progress with notable advances in the technology. Devices are now being deployed into the harsh marine environment with a good degree of confidence in their expected performance, and with the benefit of sustained periods of operation at sea, both in terms of the data and the information that's being collected, operations and maintenance understanding, and also proving that they can survive this environment. And the technology has now also been proven to be able to deliver consistently into the grid. Industry pioneers have successfully funded and deployed first arrays such as the Nova Innovation Blue Mull Sound Array in Shetland, the world's first fully operational grid-connected tidal array, which we'll be hearing more about this afternoon, and also the Maygen project in the Pentland Firth, the world's largest tidal array at the moment. And we've also seen production milestones such as Orbital Marine Power's 2 megawatt device, the world's most powerful tidal turbine. To continue this exceptional progress, we need to continue increasing performance and reducing costs, and this is where the Element project comes in, making use of advanced control methods. The UK and Europe are well placed at the forefront of the technology development, with a variety of active developers, a strong supply chain, and unrivaled test centres and demonstration zones. Current generation of devices are converging on either a 2 or 3 bladed rotor configuration, as you can see on the left hand side, and although early turbines may have had a monopile, the most recent deployments have relied on either a gravity foundation or indeed a floating hull, as you can see on the right. And just to complete this introduction section, ORE, Catapult and Nova Innovation have been successfully collaborating as project partners for a number of years now, particularly on the ONFET, which is Enabling Future Arrays and Tidal project, T2T2 project, and now Element. We've covered quite a wide range of work with them, which covers project communications and dissemination, marine offshore operations, and then also looking at the Shetland array resource and weight modelling, which required ADCP and ADV deployments, turbine load monitoring and instrumentation. And as part of the D2T2 project, we've previously tested a turbine at our facility in Blyth. Okay, and that's a good point to hand over to Colin Walker, who will now describe the role of the Shetland tidal array in the project.
Thanks, John. Yes, I'll just share a quick introduction to NAOME Innovation and where we're at in our technology development to help provide a context for the role that Element has for us as a company. We have our head office and manufacturing facility here in Edinburgh in Scotland, but we also have colleagues spread out in Shetland, Wales, and most recently Canada. We just celebrated our 10th birthday as a company last month, and in those years we have been continuously developing our tidal turbine technology. We started with a 30 kilowatt prototype device and then designed, built and deployed 3 of our 100 kilowatt M100 devices in what became the world's first offshore tidal array at our Blue Sound site in Shetland. Following this successful delivery, we were able to secure funding to further develop our technology, and so we started to investigate in direct drive technology, and that started with a 50 kilowatt device, and this was based on technology progression observed in the wind industry, but also our drive to improve turbine reliability by removing gearbox and oil and associated cooling systems. So the results of that initial endeavor into direct drive were very positive. So we built on this in further projects on D2T2 and TIPA, both developing that direct drive technology further. This led us to further mature that technology, as well as continually improve many other aspects of our turbine systems, and ultimately moved our technology further towards commercial readiness. Our flagship ONFET project that John mentioned has consolidated these technology learnings into our new M100D turbine, and the ONFET project will add 3 of these devices to our Blue Sound site, ultimately giving us a product that we can take to any future commercial array, such as our new array project in Nova Scotia at the Bay of Fundy in Canada. The next slide, please. As well as the technology within the turbine itself, we've developed other aspects of technology associated with tidal energy for ultimately delivering renewable energy to the grid. One such project was our energy storage project in partnership with Tesla, where despite the variable power production from the tides, we are now able to provide a constant base load delivery of power to the Shetland grid from our turbines using battery storage and our in-house developed automated power dispatch controller. So we're not just developing the turbine hardware itself, but at NOVA we have a holistic approach to making tidal power a practicable and competitive option for renewable electricity production. For example, we've also got a live project developing right now, a improved subsea electrical connector for marine renewable energy devices. So all these different aspects come together with the turbine itself. Next slide, please. Having said that, the turbine itself has always remained the central focus for our technological advancements. And ultimately, this is what makes the money. It must be demonstrated to perform reliably and survive the harsh marine conditions of high flow energetic sites. Should be a few pictures of that, Audrey. I'm not sure if it's going to be on another click. But after learning many lessons, yeah, thanks, from these, the 3 projects are represented on the screen there. We believe that our current hardware design is capable of what we require from it. It's in a good place and it's been matured over several years. We've also been doing some developing of the turbine control system in each of these projects, but Element gives us a unique opportunity to advance that maturity of our control system at a faster rate. Taking the progress that we've made in our hardware development, we can now ultimately make advancements in our control systems to ultimately get more out of what we already have. And I'll talk more about that later and how Element does that for us. Okay, I'll now pass over to Dr. Hong Yu.
Thank you, Colin. I'm Hong from University of Strathclyde. As I mentioned earlier, we are involved in the Element project, mainly looking after behavior modeling. And Strathclyde University, we have been awarded the University of the Year twice, and also in this year, we've been awarded Scottish University of the Year and the Queen's Anniversary Prize. For this project, mainly is 2 departments are involved. We have colleagues from the Department of Electronic and Electrical Engineering, that's EEE. And we also have colleagues from the Department of Naval Architecture, Ocean and Marine Engineering, NAOME in short. So these 2 teams together actually brings the UK's largest cluster of researchers in offshore renewable energy. Next slide, please. So first, I start to introduce my research center as Wind Energy and Control Center in the EEE department. And this is a research group focusing on renewable energy and also control. So we do teaching research in various fields, in mostly in wind, but also in other renewable types. For example, the dynamic analysis of turbine systems, modeling, simulation, control system design and optimizations, etc. And also we look at resource assessment, condition monitoring, etc. And there are other areas like a wider covering of complex and nonlinear systems. Next slide, please. Within the EEE department and also in collaboration with other colleagues within the engineering faculty, we run the EPSRC Center for Doctor Training. This is we have a history here starting from the first doctor training center in wind in 2009, and then we progressed to the CDT in wind and marine. Now we are in the 3rd stage of the doctor training center, so we further expanded to wind, marine system and structures. So for these centers, we have expertise from wind energy and offshore structures from Strathclyde University, and we have marine energy people from University of Edinburgh, and also experts from offshore structures at the University of Oxford. Next slide, please. So within these doctor training center, since we cover a wide spectrum of the offshore renewable energy, including wind, wave, and tidal energy generation, I just put a few key courses we've covered within the program. And it can be seen that it actually covers the most crucial areas in recent offshore renewable energy development. Next slide, please. It's worth mentioning that we also have colleagues from the NAOME Department. And the NAOME Department is right now the world leading center of marine technology. They have the largest European team in research and teaching. I think now they have around 130 academic staff members with research students. Next slide, please. In the NAOME department, they have excellent experimental facilities which can be used to provide testing services to the UK tidal and wave energy system. And it's also used for teaching and research purpose, also for some modest scale of commercial applied wind testing. And next slide, please. Within the Wind Energy Control Center and also with the CDT, etc., we have in recent years, more than recent, in the past decade, quite active in various renewable energy projects. And here in these slides, I put some most recent information from our project funded by EU FP7 H2020 projects and also by UK EPSRC support. So it is still a very active and growing area within the center. Thank you.
Thank you very much for that, Hong, and to John and Colin for completing our introduction to scene setting, tidal energy, and the project element. So now we're going to move on to a bit more detail on elements, goals, and innovations. And can I just remind everyone to put your questions into the Q&A, and we'll come back to them at the end of the webinar. Thank you. Sorry, so first up is Colin Walker, please.
Thanks, Audrey. Okay, so I'm going to try and summarize the whole element project in less than 10 minutes for you. So bear with me if it feels like there's a bit much. I will focus on a few particular areas, and Hong and John will add to that as well. So the element project is made up of the 11 European partners shown there on the screen. At the heart of the project is the design of a control system and behavioural modelling. These two aspects are linked together throughout the project, as the design is used to create the model, and modelling outputs are then fed back into design to make improvements in the design, and you'll see where the test aspects come in as well. Having completed the initial design and initial modelling to date, we're just about to commence the prototype build phase of the project in coming months, where we'll be using our 50 kilowatt device that you saw on one of my earlier slides. We will implement the newly designed control system into this turbine, and then we'll conduct 3 separate testing phases with it, as well as a final test phase using one of our deployed M100D turbines. Each of these 3 test phases is designed to allow us to assess the control system and feed results back into design and modelling work to make those iterative improvements. So this means that the project learnings will be accumulated throughout the testing phases and result in a finalised control system at the end of the project in 2022. In parallel to these tasks, we have important work being conducted on third-party verification and commercialisation, environmental assessment and improvements, as well as socioeconomic impact appraisals. I'm going to focus a bit more on the control system design and show its importance, not just within Element and to the partners that are involved, but also how it contributes to the wider goal of commercialization of the tidal industry. You go to the next slide, please. I think you might need to click again. My PowerPoint skills let me down there. One of the main unique aspects of Element is the fact that we aren't having to invest significant capital to make improvements in the control system. So at the moment, most of our turbine cost is associated with the turbine structure, the drivetrain components, etc. Basically all of the hardware that we have to put in the sea. But once we've developed a control system, there isn't much marginal cost involved for changing one control system out for another. And that's because these changes are predominantly software based. Maybe sometimes we'll require some new sensors or minor hardware changes, but most of the changes are in the software, and as a result don't bring with them an additional capex cost, and therefore our existing turbine design remains at the same cost even with these improvements added in. The other unique aspect of the project is that we aren't starting from scratch in this area of control system improvement. The wind industry has been here long before us and to a lot of extent continues still to work in this area, but the Element project is looking to bring the experience that our project partners have from that industry, and also bring the knowledge over from the wind industry control to tidal turbine control. Ultimately, the principles and concepts of control are common between the two applications. But where Element adds value is that by transferring these learnings from the wind industry and then tailoring them to meet the nuances that tidal presents, we can make the most of those learnings that wind has already made before us. Go to the next slide, please. So what do we mean when we mention the turbine control system? Well, it is quite a broad term, but basically it covers anything within the turbine that's involved in controlling operation of the turbine. If you focus in a little bit to the fundamental operation of a turbine, it's to deliver power to onshore by controlling aspects such as the speed and torque and power of the turbine. And this fundamental aspect of controlling the speed and torque and power, we call the turbine controller. And it's particularly complex. And it's a specific area of focus for the Element project. All of this decision making has to happen constantly and at a very fast rate. If you think of traditional thermal power stations, you've got the opportunity to throttle or control the fuel, whether it be coal or gas or whatever, or even in hydropower, controlling the water flow. You have control of that into your system. And so when you want to power down, you can throttle that fuel supply back. But like wind, in tide, when we're working with nature, we don't get to control what we're presented with, and we can't control the tidal flow. So this effectively means that the turbine is flying blind. It doesn't know what's going to come up next. And so therefore it has to constantly be reacting to the power produced by the turbine rotor as it spins. To put it another way, between the time of me clicking my fingers, our turbine in Shetland will have calculated and changed the speed and torque of our turbines over 20 times between each click. And so what is a very fast decision requires very accurate information and intelligence to make the right decision. And so this is where the complexity arrives. There are also other parts of the control system beyond this, such as processing all the sensor data gathered from the equipment and environment inside the turbine to ensure that everything is functioning as it should, and therefore power generation can safely continue within the turbine. There's other obvious things as well, active control of, for example, measuring a temperature and deciding if a cooling pump or fan should be turned on or turned up, gathering accurate data from the turbine subsystems to ensure that the device is operating within its design specification. The turbine also communicates with our onshore array controllers, and therefore it's receiving commands and parameters from it constantly. It's even calculating when the tide flow is sufficient to start up the turbine at the right time, as well as lots of other features that go beyond this. And so all of these features have to be designed into the turbine, and then they have to all run continuously and autonomously. Once we deploy and commission our turbines, we only ever have to interact with our turbine when the control system has decided that an anomaly, easy for you to say, has occurred that it doesn't know how to respond to. And in that event, it simply shuts the turbine down and flags the turbine up for the attention of an engineer. And in most 99% of the cases, the engineer will go along, assess the data that's being gathered before they shut down, see what the issue was, and then usually decide to safely restart the turbine. And so the control system takes over again, and it can, as I say, run entirely autonomously. So with so many control responsibilities and options available, the control system not only has to make decisions that keep the turbine operation stable, but it also has to make the optimum decision when taking into account various factors, some of which I've shown on the right-hand image on this slide. And think of it like this as well, like this might help. Just as you need to decide how to control your car to not only get to your destination as quick as possible, you also need to balance that with not burning out your engine or not damaging the suspension by going too fast over uneven or bumpy ground. You need to take into consideration the other road users, operate in harmony with them. You need to make observations about the conditions around you and the condition and capability of the car that you're in. And with all those factors in mind, adjust your control of the car appropriately. And as humans, we're very good at making these types of trade-off decisions. And we do that by assigning value to the various factors involved and then responding appropriately. And so the choices are there in a very same manner for operating a turbine. Information must come in and you must make a decision on how you respond to that. Operating for maximum electricity production, for example, may seem like an obvious approach to making more money. But what if that costs you an extra 1 or 2 unplanned maintenance events over the turbine life because you've pushed it so hard? That's expensive for those maintenance events, and it may cost you even more than the extra revenue that you generated. But similarly, taking an overly cautious attitude may give you a turbine that operates easily for 20 or 25 years, but then struggles to be commercially viable in the important early payback years of the project. And so this is where Element seeks to produce a control system that strikes the right balance between all the factors involved. And those are really just 2 that I've outlined. There's other ones on the screen that come in to make that decision a bit more complex. So that balance as well may not just be the same throughout a lifetime. It may be different for the same turbines different turbines within one array, based on their individual performance, based on their service histories. But that's the goal of where we want to get to, a control system that can manage all of these factors, all of these variables, and autonomously make the preferred decision. We go on to the next slide, please, Audrey. That just outlines some of the tangible objectives for the project. These are specific targets within the project that ultimately all result in a reduced levelized cost of energy. That's the main measuring rod, if you haven't heard that term before, for where the industry and technology are at. That LCOE reduction that we're aiming for, that 17% reduction, is made up by a modest improvement in energy yield, that's electricity produced, a reduction in OPEX through improved reliability, particularly around the area of reducing variations in loads that the turbine experiences, and therefore reducing fatigue loading of the turbine structural components, which also contributes to a lifetime extension, where we also want to increase the lifetime of the turbine by improved management of the turbine as it ages. In other words, the same way as you drive a 15-year-old car a bit differently from a brand new car, it's that kind of approach that we're wanting to build into our control system. And ultimately that can produce a reduction in LCOE. That's the graph on the right-hand side shows the European Union targets over the next decade. And we've got quite an ambitious target in Element. And so we believe that this 17% is achievable, and that will keep us on track to achieve these EU targets, particularly the upcoming one for 2025. Okay, that's probably enough from me. I'll now hand over to Dr. Hong Yu.
Thank you, Colin. Okay, Colin has mentioned the control challenges for the tidal turbine systems. And as you can see, that there are various factors to be considered for the turbine system. And then how do we consider to balance all these important factors in the same system? And one option is to establish a holistic numerical model that includes the different subsystems into the system. And we are hoping that such a behavior model can be used to test and tune the control systems over a wide range, covering the different turbine size and the different supporting system to the turbine system. And also we wish to see the performance in different testing sites, say onshore testing, tow testing, S3 testing, offshore testing, etc. And then I need to echo Colin and John that the tidal turbine system operate in a very harsh and also uncertain environment. So if we hope to improve the control system performance for such a system under a highly uncertain environment, we need to take into account data information. And the data information can come from the new measurement technologies and also from new estimation techniques. For this project, we are going to explore the emerging technologies in learning, data-driven learning. And we believe that this will largely improve the control system performance. And for this system, we've just passed the design stage, and we look at the basic functions of the current control systems and the modeling functions, etc. And then we will move to advanced behavior modeling and advanced control system development. And all these developed technologies will be tested in different site conditions. And then in the later stage of the project, we hope to refine and extend the behavior model to incorporate more complex aspects and also those new findings and results from the testing and control system result. So now I'm going to talk a bit more about the learning algorithm. These are the key feature of the advanced control system development. And by learning algorithms, and in some cases, we put it into artificial intelligence category. And it's a method to make use of the data information available. And then using those data, and we hope to develop a better understanding of the system operation in the dynamic context, in the changing and uncertain environment. For example, we can use a matured technique, which is called extended Kalman filter, in this case, to estimate information such as the float field and also some other key information that cannot be directly measured. And we can also use a data-driven method, which is called Gaussian process, to estimate information such as the maximum efficiency power coefficients, the anomalies, using available scattered data. These are all very useful techniques and has been discussed in wind industry. We are hoping to bring this to the tidal turbine system. Next slide, please. Audrey, next. Okay, right. This is a configuration of the behavior model system. I'm putting here a very simplified version, mainly to give you a flavor what is included in this behavior modeling system. So if you look at this configuration figure, in the central part of the system, those dark blue blocks are developed in the first stage, as we call initial behavior modeling. And in the very central part of this modeling system is the turbine model itself. And the turbine model takes input from the far-field hydrodynamics part, and also with in the first stage with a simplified structure supporting model. And this information can provide the simulated measurement data that can be used for the controller design. And the controller, of course, will give guidance or instructions to the turbine system for the operation. And then for this system, the core turbine model can produce output that is used for calculation of the energy generation, and also to evaluate the loading performance to see to be used for the damage model. And these information are very crucial to estimate the overall performance of the system. For example, one of the key objectives for this project is to achieve 70% of reduction in the levelized cost of energy. And that can be calculated from the behavior model using the energy generation, the estimation of the load, and also using some baseline information from the capital expenditure and operational expenditure. And all this information can be used to further optimize the choice of the controller, the setting of control parameters, etc. And these are covered in the initial behavior modeling stage. And then if we wish to go for more ambitious targets like those mentioned in Colin's slides, for example, we also hope to keep the system running without with a harmony existence with sea animals. And then we hope to include more information to support the control system. For example, one key block we consider here is the collision risk model, which can be used to develop the automated collision avoidance system. And that is very crucial for the tidal turbine operating in the undersea environment. And the controller itself is going to be enhanced by those new techniques such as learning algorithm based on data technology and based on also on the model itself. So this is the overall configuration. Next slide, please. For the Elephant project, we have a different work packages for control and also for behavior modeling. They are closely linked together, and the control target itself, we can put the control at different levels. For example, at the supervisory control level, and also at the operational control level. I just put one recent slide here to show a part of the supervisory control. And in this case, for the tidal turbine system, we can consider, if say we look at the start and stop operation at the supervisory level, and a reasonable logic is to put it into several stages, including the 2 startup stages, 2 shutdown stages, and 2 park stages at high and low flow speed, and 1 shared normal stages in between. To design a proper control logic to support the startup and stop of the tidal turbine system, in principle, we need to estimate the flow and make decisions based on the reliable estimation of the flow information. And these can be supported by various techniques. One of them, which is highly regarded in wind industry, is to use a Kalman filter to estimate the flow information in a short term. So that is going to be investigated in this project.
Yeah, thanks, Hong. And so on this final section this afternoon, I'll give an overview of the work packages for testing, particularly the onshore testing work package. So the testing and demonstration of the element controller consists of 4 key work packages, starting with the onshore testing, and then it will progress through the tow testing and estuary testing, which will happen at Tidal in Brittany. And then finally, the controller will be deployed on the turbine in the Shetland Tidal array. So MW Catapult will be delivering the onshore testing work package at our test facilities in Blyth, and this is scheduled for April and May 2021, so next year. So the key benefits of including the onshore testing in the programme are being able to perform a performance appraisal under very controllable test conditions. This helps to de-risk the future offshore operations in the following work packages. And you can imagine it's a lot easier to address any issues and findings onshore than once you've deployed offshore. Also with testing, you've got the ability to cover a very wide test matrix, and you can control the point of your test, like Colin alluded to earlier. Tidal flows are very variable. During your testing onshore, you get out what you put into your test rig. And that will give the opportunity to adjust or optimize the test controller before going on into work package 9, 10 and onwards. The test results from the onshore testing will be independently verified prior to that, and the findings will be invaluable for informing that future work. Okay, so just a very quick background to our test capability at MW Catapult. So we operate the most comprehensive, open access and independent test and research facility anywhere in the world for offshore renewables. And we use our expertise to help develop the next generation of these technologies. And these test and validation activities fall under 4 key areas. So blades, powertrains, electrical infrastructure, and operations and maintenance, technology, test and validation. So the area that we'll be looking at for element is powertrain testing. So the 1 MW Powertrain Test Rig is being developed, test and support the development of sub-megawatt, so below 1 MW systems and sub-components. And these tests typically include endurance and extreme load, system performance tests, and system verification and validation, and also improvements to the physical and numerical models, such as condition monitoring validation. The rig itself, which you can see in the bottom right-hand corner, it simulates the operational, mechanical and electrical loads that you'd expect the test piece to experience in operation. And it's a modular design which provides a great flexibility to accommodate a diverse range of devices and test configurations. So what you can see in this picture at the bottom right is the test bed with, at the far end, a support frame holding motor gearbox, and then the flange for the shaft adapter. And basically it's a 940 kilowatt motor with a variable speed drive, and we've got the option of speed or torque control, and we've got a gearbox which can provide speeds on the low speed shaft of up to 95 revs per minute. Got a full suite of instrumentation, including torque and speed measurements, which are used for the controller feedback, and everything's output through to a 50 Hz 400 volt distribution board. And obviously it's all controlled by SCADA systems. That's for the data acquisition and the control, and that all includes the essential safety protocols for the test. And so on the next slide, we've got a brief description. So a new feature is being implemented specifically for the element project is the ability to conduct hardware in the loop tests. So hardware in the loop is a technique where signals from the controller are connected to the test system to simulate reality. So in this case, the rotor from the turbine is removed, and the hill controller provides a signal which represents what the rotor would do, and the element control system is tricked into believing that the rotor is installed. This allows the shaft speed or torque to be controlled under time varying tidal flow conditions. We've got a flow model which is used to determine the turbine behaviour in different tidal flows, and this will include the effects of flow shear and turbulence, such like. Following commissioning, we'll do a series of baseline performance tests, and that will then be followed by the element hardware in the loop control system tests. And this will allow an assessment of the performance to be made and to show what improvement we're getting from the element control on board. So in the final slide, I've given an image of what this test rig will look like. So it's some bespoke hardware to be able to position the turbine on the rig correctly. So you can see on the right hand side the NOVA test piece in the white casing. And we've got a connection through into our test bed in the frame. In the middle we've got a flexible coupling which includes the customer hub, and that allows for the low speed shaft of the test piece to connect into our gearbox. Like I said, very flexible setup, and that has allowed us to be able to do what is required to test element controller. And this is a fairly unique test asset, and the Onshore test program will help play a role in accelerating the development of the innovative technologies that we're looking at in the element project. And that will help to harness the clean, abundant and predictable tidal energy flows that we see around Europe. So let's pass back over to Audrey for questions and answers on the project.
Thank you very much, John. That was great. Thank you also to Colin and Hong. We have some questions in, so we'll just dive straight into them. We have the first question: is there a great difference of current force at the top versus the bottom of the turbine? Does that impact the control, or is it negligible? I think that's probably one for Hong or Colin.
Yeah, I can start on that. There's a risk here, and you get an electrical engineer talking about hydrodynamics. Well, I'll get my stab at it. Yes. Ultimately, yes, there is a variation. John just mentioned at the end of his presentation there about the shear profile within the water column. That's the effects of that shear profile and how much faster the flow is near the surface than the bottom is dependent on a lot of factors, including topology and kind of water depth and your channel, your width and size and things. But yes, you do get a change, and it's something that we have to be aware of in our turbines. NOVA's particular turbines are two-bladed rotors. So when you have the rotor aligned vertically, you have one blade which is obviously highest in the water column and the other that's lowest in the water column. And so that does give you a variation in loading across the blade surface as a thrust component, but also it gives you a variation in torque generating loads. You will get more torque where the flow is higher. And so, yeah, that does need to get built into our control system. Our controller needs to be aware basically of the potential for that. So we call it a kind of 2P effect, where twice per rev you've got one of these blades passing through the height of the water column. And so therefore, when you get to that point in the position of the rotor, you need to be expecting more torque. And so there needs to be filtering and things built into the controller to basically allow for that increase in torque or thrust components to not necessarily trick your controller into thinking that that's going to continue to happen. So when it sees these kind of pulses coming along, it knows not to jump to too quick a response to those effectively. It does also have an effect on the structural loading of the device, and again we build that into the design components. But in terms of the control system, yeah, it does get allowed for. And the modeling work is very important in that. The software that does kind of allow you to provide a measure of how much that shear effect is. And so when you're modeling that, that's one of the things that we will maybe try and get a little bit of testing out of, is to take our model and take our actual testing data and see how well those compare. As I say, electrical engineers stab at that, but hopefully if anyone else wants to add any more, they're welcome to correct me.
That's great. Thank you, Colin. Hong or John, do you have anything else to add to that?
I think that's a perfect answer, and certainly these characteristics needs to be included in the dynamic modeling of the turbine system, and that is included there.
The only other thing from a hydrodynamic side to add would be you've got a faster flow at the top of the water column, slower at the bottom. So as the blade passes through it, the force acting changes with the square of the velocity. So you can imagine a small change in velocity changes the dynamic pressure on the blade, but which in turn also changes the lift and drag forces acting on the blade at that station as well. So it's a balance between, as you go faster, your angle gets, sorry, wrong way around. So it's a balance between the force coefficient and the speed, which overall give the higher loading at the top.
Thank you very much, everyone. And it's now just past 3 o'clock, so I think we need to wrap up. But I'd just like to thank the whole panel for your really interesting presentations today. Thank you to everyone who's attended the webinar. We will post today's webinar on our YouTube channel and we'll email the link over to everyone to the addresses that you registered on. And if you have any questions that you think of after the event or that we didn't answer today, can you please send them to info@ore.catapult.org.uk. Just in case you want any more information on the project, you can go to our project website, which is element-project.eu, and you can follow project updates on LinkedIn and Twitter using our handle @ORE-Catapult. Please also look out for next month's webinar, where we'll be joined by other speakers from NOVA. I'm not sure, Colin, if it's going to be you again or if we've got somebody else from IDETA and from France Energy Marine to discuss the socio-economic and environmental monitoring work that we're doing under the project, and also the work that's underway to scope out new tidal energy sites in France. So once again, thank you very much everyone today for joining us, and have a good afternoon.